Hello and welcome to this lecture on the applications of Laplace transforms. In this lecture, I shall carry the discussion forward from my previous two lectures, wherein I had discussed, I had given an introduction to the notion of Laplace transforms, and we explored the properties of the said Laplace transforms. So this is part of module 3 of your course in Mathematical Physics 3. So this is going to be the outline of this lecture. So it'll be first we'll have a recap of whatever we had done earlier by having a look at the table of Laplace transforms. Then I'll introduce you to the notion of inverse Laplace transforms, which helps us to easily find a solution to many otherwise difficult problems. Then we'll do some few examples, some selected example problems, followed by some physical applications, that is the simple harmonic oscillator, the damped oscillator, and when you apply what happens when you apply an impulsive force on a object. So this is basically, to recap, this is what a Laplace transform is. So if it gives you it allows you to transform from one function to another function. So suppose I have a function f of t. Then from this function f of t, you can go to another function capital F of s, and the relationship between them is via this integral transform. And in this integral transform, the lower and the upper limits are 0 and infinity, and the kernel function is e to the power minus st, and I could represent this as L of f of t. Okay, so over here s is, of course, I'm assuming it to be real. So whenever you talk about Laplace transforms, there is going to be a particular value s naught, such that for values of s greater than s naught, this integral will exist, and for values of s which is less than s naught, this integral is going to not exist, is going to diverge. So as a result, we will have Laplace transform defined only for those values of s which is greater than this particular value of s naught. So we had discussed the properties of Laplace transforms in the previous lecture. So we had lots of properties. I suggest you can go back to that lecture to find out how we had discussed these different properties. So we had the linear property, the Laplace transform of derivatives, the Laplace transform of integrals, the substitution property, the translation or the shifting property, the change of scale property, the derivatives of Laplace transform property, the integral of Laplace transform property, and finally the convolution property. So using these different properties, we had obtained the Laplace transforms of some very common functions, and I have summarized all those results that we had derived in the previous classes, previous lectures, as well as the ones which I had left to you as assignments. So I have summarized in this table. So in this table, the first column is a function f of t. The second column is the Laplace transform capital F of s. So whatever you use in the second column, that is basically the Laplace transform of whatever is in the first column. So if you recall, so if the function is a constant function, that is f of t takes a same constant value k, then its Laplace transform will be k by s, and this is going to be valid for values of s which is positive. For t to the power n, the Laplace transform can be written in terms of the gamma function, and so on. So we have these different ways by which different expressions for the Laplace transforms for these common functions. Okay, so so we have already derived many of these, and then we have used some properties. For instance, we had used the for instance, in, let's say, in this case, okay, so we had used this property, the derivative of Laplace transform, to obtain this one. Similarly, we had used the same property to obtain this one using the cos and sine. So we can derive all of these properties very easily. Starting from some few basic functions, we can derive all of these results. Okay, so now we go to the idea of an inverse Laplace transform. Okay, so to understand inverse Laplace transform is basically this. If suppose, let's say for instance, I take this e to the power kt, okay, the Laplace transform of this is 1 by s minus k. Okay, so if this function is the Laplace transform of this, then this function will be the inverse Laplace transform of this function. Okay, so I can write that L of e to the power kt is 1 by s minus k. In the same way, L inverse of 1 by s minus k will be equal to e to the power kt. Okay, so if capital F is the Laplace transform of small f, that is capital F, can be written as an integral function with this kernel and these limits, then the inverse of the Laplace transform is such that here in this case what is given to us is the function small f, and what are we finding? We are finding capital F. If it's the other way around, instead of knowing small f, if we know capital F, okay, if capital F is given to us, then the small f is known as the Laplace transform of this capital F. Now the Laplace transform is unlike the Fourier transform, where you can have a explicit relationship like this. Explicitly we can write it as an integral. Okay, so we have one Fourier transform, and the inverse Fourier transform is very much symmetric. But unfortunately, in case of inverse Laplace transform, we don't have an explicit formula for the inverse Laplace transform. Okay, it cannot be derived, it cannot be determined. Such a formula like this cannot be determined for the inverse transform. Okay, so there are mainly three ways by which we can find out the inverse Laplace transform. The first is, of course, there is a general technique, and this general technique to obtain this inverse Laplace transform, it involves residue calculus. So we need to use complex variable theory to find out the general formula for the Laplace transform. Another is you could have a numerical representation of both the Laplace transform as well as its inverse. And lastly, the easiest way is what we will be following, that is by using a table of transforms. You see, we already have a table of transforms like this. Okay, we already have a table of transforms like this, so we might as well. So if I know that this one's Laplace transform is this, then this one's inverse Laplace transform must be this. So we already have this result, so we could have a table like this, and using these different properties we can easily find out the inverse Laplace transform of any function. Okay, so this is the table of Laplace transform which we can use to find out the inverse Laplace transform very easy. So it's just a matter of reading, just like you look into a dictionary. In the same way, you could just look up this table like as if you're looking into a dictionary and finding out what is the inverse Laplace transform of that function. So we'll see that using a few examples. So let's say this is the first example. I want to find out the inverse Laplace transform of this function. Capital F is equal to k square by s into s square plus k square. So over here it's a function of small s. Okay, so that means this k must be a constant. Okay, so we want to find out the inverse Laplace transform of this one. Now first thing that we need to do is go see in the table if such, look in the second column, if we have any such function k square by s into s square plus k square. Do we have any function like this? Unfortunately, we don't have any function like that. Okay, k square by s into s square plus k square. We don't have any function as such in the second column which exists. Okay, so now we have to do some kind of manipulation first. So we'll use the method of partial fractions. So if you recall what is partial fractions, we can write down this in terms of two fractions. The first fraction involves the first term in the denominator, and the second fraction involves the second term in the denominator. Okay, second factor in the denominator. So k square by s into s square plus k square, we can write it as a by s, because s is the first factor, so a divided by s, and the second factor is s square plus k square, so b, that we call it as b divided by s square plus k square. So now it's just a matter of finding out what are these unknown coefficients a and b. So what we do is we just add these two fractions together. So again, in the denominator we'll have s into s square plus k square, and then a will be multiplied by this, so a into s square plus k square, plus b will be multiplied by this, which is into b into s. Now what we do is we collect the k square terms and the s terms. Those terms which contain k and those terms which contain s, we'll collect them separately. So a into k square, there is only one term, so we have ak square. Then there's going to be an a square, as square, and there's going to be a bs, so that we'll collect it together. Okay, now we compare both the left hand side and the right hand side. The denominator is same, so we just need to compare the numerators. Okay, so from here we see that with k square we are multiplying 1 with k square. Okay, so it means, and here a is multiplied with k square, that means a must be equal to this 1. Okay, and there is no s term, that means this entire quantity, okay, this entire quantity must be equal to 0. This entire quantity is 0, and we have just found out that a is equal to 1, so it means 1 into s square plus bs must be equal to 0. So that means b will be equal to minus s. You can just work this out yourself. It's a very simple, straightforward calculation. So a is equal to 1, b is equal to minus s. Now plug this back in to this. Okay, so we'll put a 1 here and we'll put a minus s over here. So this will give us f of s is equal to, which is k squared by s into s squared plus k squared, which is equal to a by s. A is equal to 1, so 1 by s. B is equal to minus s, so minus s by s squared plus k squared. So now we just need to find out, if you want to find out the Laplace transform of this, we need inverse Laplace transform of capital F. We need to find out the inverse Laplace transform of these. Okay, so capital F of s is basically this. So if we take throughout this, if I take the inverse Laplace transform, so inverse Laplace transform of capital F is equal to inverse Laplace transform of this one, which is equal to inverse Laplace transform of this minus this. Okay, now the linearity property is applicable to inverse Laplace transforms also. So I could just open this up and I could write it as inverse Laplace transform of 1 by s minus inverse Laplace transform of s by s squared plus k squared. Now we need to find out the inverse Laplace transform of this and inverse Laplace transform of this, which we can again now look into the dictionary, that is the table of Laplace transforms. Okay, so if we look at the table of Laplace transforms, we find that we can use for the first one, okay, so 1 by s, we can use this first entry because Laplace transform of k is k by s. If I take k equal to 1, then inverse Laplace transform of 1 by s is equal to 1, right? Inverse Laplace transform of 1 by s is equal to 1. So 1 by s, k is 1, so there will be a 1 here. Again, so we'll have here s divided by s squared plus k squared. S divided by s squared plus k squared, it exists here. So this one's inverse Laplace transform will be cos kt. Okay, so this one's inverse Laplace transform of 1 by s is equal to 1, and inverse Laplace transform of s by s squared plus k squared is cos kt. So this gives us the answer that we are looking for. The inverse Laplace transform of this is equal to 1 minus cos kt. So again, I'll like to recollect this chart, the flow chart that I had shown to you when we had first discussed integral transforms, when we had done, I think it was in the lesson on Fourier transforms. So suppose I have a problem. Why do we really need integral transforms? Suppose I have an original problem, okay, to find out the solution of the original problem, the solution is really difficult. So in that case, what we do is we take the integral transform and we translate the problem in the transform space, and then we can find a relatively easy solution, and then you take the inverse transform, that will give us the solution. Okay, this works actually, this route works, and we'll see that using some more examples. Okay, take this example. So suppose I want to compute this integral. Okay, now remember, this integral is really difficult to compute. Okay, so I want to compute this integral for all values of t. Okay, so you see, it's an integral of sine tx by x dx from 0 to infinity. Now t could be positive, it could be negative, it could be 0. So for all values of t, I need to find out what will be the result of this, because this, of course, after once you integrate with respect to x, this will be independent of x, so only what will remain is t. So that will become a function of t. So we want to find out what this function looks like for all values of t. Okay, now if you want to do this analytically using conventional integration techniques, this is going to be extremely difficult. You can just try it out, just try to apply the integration by parts and try to solve this. It is extremely difficult to solve. So for that, so that means the solution for this problem, the original problem was we are trying to find the integration of sine tx by x. Getting the solution, okay, it's really difficult. The way to get this by ordinary calculus, okay, by using integral calculus, the solution is extremely difficult. So what we will do here is we will take the root of the Laplace transform. So we'll use a Laplace transform and get the solution much easily and much faster. Okay, so the strategy that we will be following in this case will be the first step. There are mainly 3 steps. The first step is we find out the Laplace transform of f of t. That means we find out the Laplace transform of both the left hand side and the right hand side. We want to find out the Laplace transform of this one. Then we evaluate this integral in the transform space. Okay, now what is the transform space? You see, this function, it's a function of t, so the transform space will be a function of s. So the function of s. Okay, so the space which contains values of s, that is the transform space. then this same integral we will evaluate not in the t space, but we will evaluate in the s space. And once we get the integral there, we just need to take the inverse Laplace transform of the integral. That will give us the solution. So let's proceed here. So what we do is we do the first step. The first step 1 and step 2 we'll do it together. Okay. So what we do is we take the Laplace transform of f of t. So Laplace transform of f of t is equal to Laplace transform of this integral. So now we are considering, in this case we'll just assuming for the time being, because we want to find out for all values of t. So we'll just assume that t is positive. Then we will see, we'll see how the answer looks like, and then we'll be able to actually figure out what will happen in the case of negative t and 0 values of t. Okay, so we'll take the Laplace transform of this particular equation on the both left hand side and the right hand side. Now we just write this down, expand the Laplace transform, because Laplace transform is whatever you put inside the bracket, you have to put it inside a integral transform. So the integral transform is 0 to infinity e to the power minus st, that's the kernel function, and whatever is inside the bracket, this entire integral itself, we'll just put it over here, integrated with respect to t, because that's the Laplace transform of f of t. Now this x and t, they are independent, so I could always exchange the order of integration. So here first we are integrating with respect to x, then we are integrating with respect to t. So I could just swap this integration. So I could take this integration with respect to x, I could take it outside, and the moment I take integration with respect to x outside, that means this 1 by x also I can take it outside. Okay, because whatever remains depends only on t, sine t x e to the power minus st dt. So it depends that rest of the terms they depend only on t. So that quantity which depends only on x, I could always take it outside. So 1 by x, then what is left is integration, that is this integral 0 to infinity e to the power minus st, sine t x is left dt, and of course this dx comes outside because I have changed the order of integration. Now when we look at this, okay, immediately we can recognize this. We are integrating 0 to infinity e to the power minus st sine t x. So this we immediately know that this is nothing but the Laplace transform of sine t x. We already know this is the Laplace transform of sine t x. So we just refer to the table. We just refer to that table. Yes, we refer to that table. Okay, we just pick up the Laplace transform of sine t x, okay, x is a constant here. Okay, so x will be this k will be replaced with x, so tx. Okay, so we'll have a x divided by s square plus x square, x divided by s square plus x square. Okay, so x divided by s square plus x square. So this will be the result. Okay, this integral, this is the result. So you can see how easily we have been able to evaluate one of these integrals. At first it looks like, I mean, this is going to be a nightmare because we have a double integral here, but just by recognizing that this is actually a Laplace transform and using the table, we were able to get the answer very straightforward. So x divided by s square plus x square. Now this x will get cancelled, so this will give us dx divided by s square plus x square. Now this is an integral that we already know. It involves tan inverse, right? So this integral, it's a standard integral. You could just refer to any class 11 textbook on mathematics. Okay, you can find out that this is nothing but your 1 by s tan inverse x by s. So now we have to just substitute the limits here from 0 to infinity. So when you put here integration is with respect to x, so we have to substitute x here at the upper and the lower limit. So when you put here infinity here, so we'll get tan inverse infinity minus tan inverse of 0. Tan inverse of infinity will be pi by 2 because tan takes undefined value at pi by 2. So upper limit, this will give us pi by 2, and the lower limit, it will give us 0. Tan 0 is 0, so this will give us a 0 here. So pi by 2 minus 0, which will give us pi by twice s. Pi by 2s, that is going to be the value of this integral. Okay, so this is this integral, the value is pi by twice s. But of course we have to remember that this is by assuming that we are taking only positive values of t. Now what will happen in case of negative values? Okay, first let's just finish this problem, then we'll have a look at the negative part. Okay, so Laplace transform of f of t is equal to pi by twice s. This is what we got. So we have finished step 1 and step 2. If you look at this strategy, we have finished step 1 and step 2. So first we have found out the Laplace transform, then we have evaluated the integral in the transform space already. Now what is left is the step 3, that is we have to take the inverse Laplace transform of the integral. So we found out the value of the integral, which is pi by twice s. So that means f of t must be equal to inverse Laplace transform of this. So f of t is equal to inverse Laplace transform of pi by twice s. Okay, so inverse Laplace transform of pi by twice s, pi by 2 I can take it outside, Laplace transform of inverse Laplace transform of 1 by s. This is what we want to find out. Okay, again we can use the table of Laplace transforms. 1 by s, if I take k equal to 1, so 1 by s, its inverse Laplace transform will be equal to k, which is 1. Okay, so this result is going to be equal to simply 1. So we will get f of t, which is equal to this integral. This value will be equal to pi by 2. Of course, this is valid only for positive values of t. Now what will happen in case of negative values of t? So therefore this is what it is for positive values of t. Now for negative values of t, what will happen? Okay, if I take f of minus t, okay, if I take f of minus t, then what will happen? Sine of minus tx will be equal to minus sine tx, right? Because sine is a odd function. Sine is an odd function, so you replace the argument with a negative counterpart, then that will make the function negative. So sine minus tx is minus sine tx. So this gives us f of minus t will be equal to minus f of t. Okay, so for positive values of t, if you got pi by 2, then for negative values of t, you should get minus pi by 2. And finally, for t equal to 0, this f of t will be 0, because t equal to 0, this integrand itself will be 0, so the value of this function will also be equal to 0. So there we have it. We have these 3 different cases. For negative values of t, this integral will give us minus pi by 2. For 0 value, t equal to 0, this integral will give us 0. For positive values of t, this will give us pi by 2. So we could just express this in the form of a function like this, in the form of a graph like this. Now you can see here, this is a discontinuous function, right? It's a discontinuous function. And what does this function remind you of? If you go back to my lecture on Heaviside step function, this is nothing but the signum function. The signum function, it takes the value 1 for positive values of t, and it takes a value minus 1 for negative values of t. So all you have to do is take the signum function, multiply it with pi by 2, because it's taking the value 1 anyway. So if you multiply it with pi by 2, it will correctly take plus pi by 2 and minus pi by 2 in the 2 different ranges of values of t. So we could just write this function f of t, this integral, we could just write it as pi by 2 signum function of t. Now again, that chapter on lecture on the Heaviside step function, I had also left to you as an assignment. I had asked you to show that the signum function can be written as twice h of t minus 1. So the signum function can be written in terms of the Heaviside step function. So you can just replace this over here. So this will give us our final answer, that is f of t. This is the complete answer. F of t is equal to, which is nothing but this integral. This is equal to pi by 2 times twice h of t minus 1. So this is the complete answer. This is the complete answer for this integral for all possible values of t. So next we have a physical application of this, which is the simple harmonic oscillator. So we shall do that in the next part of this lecture.